astronomers identify 4 classes of planetary system architecture. Dr. Lokesh Mishra and his colleagues from the University of Bern and Geneva Observatory proposed that the space of planetary system architectures be partitioned into 4 classes: similar, mixed, anti-ordered, and ordered. More than a decade ago, astronomers noticed, based on observations with NASA's Kepler space telescope, that planets in other systems usually resemble their respective neighbors in size and mass, like peas in a pod. But for a long time it was unclear whether this finding was due to limitations of observational methods. It was not possible to determine whether the planets in any individual system were similar enough to fall into the class of the peas in a pod systems, or whether they were rather different, just like in our solar system. In their research, Dr. Mishra and co-authors aimed to develop a framework to determine the differences and similarities between planets of the same systems. And in doing so, they discovered that there are not 2, but 4 such system architectures. We call these 4 classes: similar, ordered, anti-ordered, and mixed. Planetary systems in which the masses of neighboring planets are similar to each other have similar architecture. Ordered planetary systems are those in which the mass of the planets tends to increase with distance from the star, just as in the solar system. If, on the other hand, the mass of the planets roughly decreases with distance from the star, we speak of an anti-ordered architecture of the system. And mixed architectures occur when the planetary masses in a system vary greatly from planet to planet. This framework can also be applied to any other measurements, such as radius, density, or water fractions. Now, for the first time, we have a tool to study planetary systems as a whole and compare them with other systems. Our results show that similar planetary systems are the most common type of architecture. About 8 out of 10 planetary systems around stars visible in the night sky have a similar architecture. This also explains why evidence of this architecture was found in the first few months of the Kepler mission. What surprised the team was that the ordered architecture, the one that also includes the solar system, seems to be the rarest class. There are indications that both the mass of the gas and dust disk from which the planets emerge, as well as the abundance of heavy elements in the respective star, play a role. From rather small, low-mass disks and stars with few heavy elements, similar planetary systems emerge. Large, massive disks with many heavy elements in the star give rise to more ordered and anti-ordered systems. Mixed systems emerge from medium-sized disks. Dynamic interactions between planets, such as collisions or ejections, influence the final architecture. A remarkable aspect of these results is that it links the initial conditions of planetary and stellar formation to a measurable property: the system architecture. Billions of years of evolution lie in between them. For the first time, we have succeeded in bridging this huge temporal gap and making testable predictions. It will be exciting to see if they will hold up. This research is described in 2 papers in the journal Astronomy Astrophysics.